Man, we're never gonna finish this project on time.
What are you talking about, man? Sure we are. We just have to close our eyes and pray for a miracle. Here, hold my hand.
No.
Come on, just do it. What other choice do we have? Come on. Okay. A Thanksgiving miracle!
How did you get in here?
Heard you two are in need of some help. A little battle of the Bulge, eh?
How'd you know?
That's not really important. We've got work to do.
Wow. So you think you can help us finish this by 1:30 in the afternoon?
Well, if all goes according to plan, we should finish this little journey in about 12 hours.
What time is it?
It's 1:30 in the morning! This is so perfect!
Come on, let's go!
So I think this is one of those times where you fall asleep at the desk and have a really awesome dream, only to wake up to a bitter and harsh reality. If that's the case, though, I'm going to let this one ride out as long as possible. I like it better here.
Alright guys, right through this door. Go on ahead. He'll get you started.
Hello, sir. We were wondering if you could tell us a little bit about making a closed-loop editing interface, and then how to perform a Delaunay triangulation on top of that.
What? A closed-loop editing software? No wonder you're having problems! Here's what you do. Take your last project, start deleting things at random. Eventually, you'll have what you want. A way to draw and edit closed poly loops. Now, do you know what a Delaunay triangulation is?
Not a clue.
Nice. Well, basically, it is a process that takes in a set of points and creates a triangle mesh out of that. All you have to do is loop through all groups of 3 vertices, find the circle that circumscribes these vertices, and just see if there are any other points in the circle. If there are not, you add this triangle to the mesh. If so, you don't. Easy peasy.
Gee, thanks, Professor. But what about performing a medial axis transform?
Oh, well, lucky for you, I already have a video clip of myself explaining that process. Let's take a look. The medial axis transform of a 2-dimensional shape is like the skeleton. It is a set of points that are equidistant from 2 or more locations on the loop. In order to create a medial axis transform, or MAT, from our mesh, we first perform a triangulation on the loop of exterior vertices. The centers of these triangles are sample points of the MAT. We then give each MAT point a sphere of some radius that is proportional to the triangle it is part of.
Who are all these people and what are they doing in my house? Let's see. Next we have to spray random points to the poly loop P. How do we do that?
Well, that's simple. Just pick a random point in the plane, and if it's in P, keep it. If not, pick another random point. Basically, while point is not in P, point equals random point.
But how do we know it's in P?
I remember. If we draw a ray from the point to infinity, and we see how many times it crosses the edges of P. If the parity of that number is odd, the point is in P.
Very good, Johnny. Alright, now we have to split up for time's sake. Alex, you'll go into this room over here. And John Michael, you can go into that room over there. Good luck.
These guys are perfect. I've never had so much fun.
Alright, here we go. Hey, excuse me. Do you think you could possibly tell me how to store a mesh as a corner table?
Ooh, corner tables. I don't do those.
Right,
Ha!
I'm only kidding. Come on in.
yeah.
So basically a corner table is just a list of corners of triangles, really. There'd be 3 corners to every triangle, naturally. But since each vertex is used for several triangles, what we're going to do is we set up a vertex table. And then each corner refers to the vertex, the number of the vertex on the table, which that's the part that stores its position in space. See? And then, this saves a lot of space and makes computation easier. So that's good. Also, we can make an O table that stores the opposites of each corner, which it does take up more space that way, but it ends up making the processing faster.
Okay. Yeah, it's pretty much what I thought.
Of course you did.
Also, what's place smoothing?
You're not pronouncing it right. Basically, you move each vertex a third of the way toward the average of its surrounding vertices.
What?
So basically, every vertex has surrounding vertices. So for each vertex vi, you take the average of its surrounding vertices, and that becomes your target vertex, v prime. Then, you move vi 1/3 of the way towards v prime. You do this to all the vertices across your table. And then, right. Well, you can move it more or less in the direction towards v prime, but I'd recommend 1/3.
Okay. Well, thanks a lot.
Hey, buddy.
Hello!
Okay, so I have this bowl.
Ooh, saucy. Nothing.
So I have this mess and I'm trying to bulge out. How do I do that?
Okay, all you have to do is assign some sort of z component to each of the vertices. How much, you ask? Well, just loop through all of the mat spheres. Find the ones that contain this vertex, and then one of these will be larger than the rest. Use the radius of that for the height of that vertex.
Of course, it's so simple.
You're damn right it is, Johnny. Now, I bet you're wondering how to mirror that bulge and then create a watertight mesh with those 2 bulges.
How'd you know?
Well, if I were you, I would just make a copy of the interior vertices and add that to the mesh. Then, give those negative z components. That way you have the mirror image. Then, reverse the order of the corners in all your triangles on the negative side, and then that makes all the triangles face outwards from the bulge, rather than the same way as the other side.
Oh.
The isolation of a triangle in the mesh is the average geodesic distance from that triangle to the other triangles. So if you have your triangle here, you'd walk along the edges to all the other triangles in the mesh. For example, say you have the mesh of a horse. The triangles at the feet of the horse are going to be much more isolated than those of, say, on the back or the belly, because they have to walk further to get to all the other triangles. Yeah, sure, computing something like this can be very costly, but in the end, it looks really cool. Okay, now it's your turn to implement all of this. You guys think you can handle it?
Let's do it!
A little too much, but that's the right idea.
80s high five!
I try to disguise